Okay, so just make sure from the previous slide that you have taken a look at this applet and just sort of played with the values of n and p and check and see what happens to your binomial distribution as you change the values of n and p. So let's just take a look at these pictures. If we just graphed our original distribution, n is 10 and p is 0.8. If you take a look at this graph, it's sort of slightly skewed to the left. Notice over here we changed n to be 20, so we made n larger. We took 20 different samples instead of 10. Notice how my graph is starting to get a little bit more approximately normally distributed. Notice when I change n to be 50, my binomial distribution looks very similar to a normal distribution. So when we have a binomial distribution, it can often be modeled by a normal distribution. There's a tipping point with n and p that makes the binomial distribution look approximately normal. That tipping point is the large counts condition, and if you've played with this applet, you've taken a look and seen, okay, well, when I change the values of n and p, when n is large and p is either small or a certain value, then it looks approximately normal. And we're going to take a look at what exactly those values of n and p need to be that make a binomial distribution look approximately normally distributed. Okay, so let's just say we have the x is the binomial distribution with n trials and successes of probability p. When n is large, okay, so when we have a large value of n, it's usually greater than 30. The binomial distribution of x is approximately normal, so that means it's going to look like, so if n is large, okay, we have a distribution that looks approximately normal. And just remember, when we have an approximately normal distribution, what do we usually talk about? We usually discuss the mean and standard deviation. So what would the mean and standard deviation be of this normal curve? Even though this is a binomial distribution, what would the mean and standard deviation be of this normal curve? Okay, well, the mean is your number of trials times your probability of success, and your standard deviation is the square root of your number of trials times your probability of success times your probability of failure. So how will we know if this meets our approximately normal condition? Well, in order to check and see if it's approximately normal, what you're going to do is you're going to take the number of the number of trials times p if that's greater than 10, and the number of trials times failures is if that's greater than 10. If both of those are greater than 10, then when you graph that distribution, it's going to look approximately normal. So we can use both the binomial distribution and the normal approximation in order to answer questions about the binomial distribution because they'll give us about the same answers. So this basically tells us as the number of trials increases, so as n gets larger and larger, the binomial distribution becomes approximately normally distributed, but oftentimes, so why would we use the normal distribution instead of the binomial distribution? Sometimes if you have a very, very large value of n, the probability formulas can get a bit awkward, so sometimes it's easier just to use the normal approximation to answer some questions. Okay, so we're going to go over an example. So in a survey, 506 teenagers aged 14 to 18 were asked a variety of questions about personal finance. One question asked if the teens had a debit card. Suppose that exactly 10% of the teens aged 14 to 18 have debit cards. X is the number of teens in a random sample of size 506 who have a debit card. So we're going to show that it's approximately binomial. We're going to check the conditions to see if the binomial distribution also looks normal. And then we're going to use a normal distribution to estimate the probability that 40 or fewer teens in the sample have debit cards, okay? And once we've decided that it's a normal approximation, you've done questions like letter C throughout the entire course, so hopefully that should be pretty easy. All right, so how can we show that it's approximately normal? So remember that we want to do bins. That's checking to see if it's binomial. Yes, they either have a debit card or they don't. Are they independent? In this case, they're not independent because they're not sampling without replacement. However, the sample size, 506, is much less than 10% of the population. So if we did 10 times 506, that's 5,000. So that means that it's almost binomially distributed because the probability once I take one person out of the population is not going to change that much. There is a fixed sample size, 506, and the S is we know the probability of success is 10% have a debit card. All right, so how do we check to see if when I graph the binomial, it's also going to look approximately normally distributed? Well, first you want to check that large counts condition that I was talking about. So this is, like I said, this is the tipping point. If NP are greater than 10 and N times 1 minus P are greater than 10, that it sort of balances the graph out of probability of successes and failures on either side, and it makes it approximately normally distributed. So if I take 506 times 0.10, 50.6, 506 times 0.9, that's those who don't have a debit card, is 455. So since they're at least 10, we're safe using the normal approximation. All right, please make sure when you're doing this that you show the numbers plugged in for N and P. Don't just say NP greater than 10 and 1 minus P is greater than 10. No, actually show what the calculations are to state that the large counts conditions works. All right, so what would the mean and standard deviation be for the normal approximation? Okay, number one, remember we always are going to state whether it's binomially distributed, normally distributed, whatever. So in this case, it's normally distributed. Remember, to get the mean of my normal distribution, I take N times P, so 506 times 0.1, so that means the mean of my normal curve is 50.6. The standard deviation is the square root of N times P times 1 minus P, which is 6.75. So if I were to draw the normal curve, it would have a mean of 50.6 and a standard deviation of 6.75. Now we're asked to estimate the probability that 40 or fewer teens have debit cards. So probability that X is less than or equal to 40, well, we're back to using our z-scores. So we're going to find our z-score. Data value 40 minus the mean, 50.6, divided by the standard deviation gives me my z-score. Probability that z is less than or equal to negative 1.57 is about 5.82%. Okay, that 40 or fewer teens in a sample size of 506 will have a debit card. So the most difficult part is just making sure you remember to find the new mean and standard deviation, because we're using the normal curve to estimate the answer. We could still get it using binomial calculations, and you could try that, and the answers won't be exactly the same, but they'll be very, very close. Okay, so let's just see what exactly does that look like if we compare it to the binomial distribution. So with the normal distribution, we said that about 5.82% of the population would have less than 40 would have debit cards. But how would we do that with our binomial distribution? The best way to do that would be using your graphing calculator. Remember, when we do our binomial distribution, binomial CDF is up to and including the number that we put at the end. Our number of trials was 506, 0.10% was our probability of success, and we want to add up, CDF is adding up everything up to 40, 0 through 40. So the probability that X is less than or equal to 40 is 0.06369. So they're off by about a percentage. They are a little bit different. So just keep in mind, this is a normal approximation to the true binomial distribution. So it's not going to be as accurate. The binomial answer is in fact more exact. So on the AP exam, you don't have to know how to use the normal approximation. You can always use the binomial distribution. That's totally fine. This is just you will see this maybe sometimes in your homework and stuff and other places, so just so you recognize where that's coming from. Okay, so now that we've sort of discussed the binomial distribution and the conditions for that, what happens if we're examining a chance process and we don't have a fixed number of trials? What if we're waiting until we get our first success? Okay, so here's some examples. Let's say we roll a pair of dice until we get doubles. All right, our number of trials aren't fixed. In basketball, we're going to attempt a 3-point shot until one is made. That's not a fixed number of trials. We'll just keep doing it. We keep guessing on a multiple choice exam until we get one correct. So once again, that's not a fixed number of trials. In all the above examples, there were no fixed number of trials. We're basically asking how many times we have to wait until we get one success. So if we're looking at examples that satisfy everything for binomial distribution except for the fact that we're waiting to see when I get my first success, this is called a geometric distribution. Okay, so how is it different? The only difference between the two is that the number of trials in a geometric distribution are not necessarily fixed. So in a binomial setting, the number of trials is fixed, and the random variable X counts the number of successes in a fixed number of trials. In a geometric setting, the goal is to repeat a chance behavior until a success occurs. So we're just going to keep rolling those die until we get a 6. That is a geometric setting. It arises when we perform independent trials of the same chance process and record the number of trials until it takes to get one success, not the number of successes in our fixed number of trials. On each trial, the probability of success still has to be the same. So we literally have exactly the same conditions as a binomial distribution, except for the fact that our trials are not fixed. So instead of using bins for geometric, we're going to use bits. So binary, there's still only 2 possible outcomes, success or failure. So we're rolling a dice. I'm either going to get a 6 or I'm not going to get a 6. Independent, so when I roll a dice, each trial is still independent of each other. One roll of the dice doesn't affect the other. T, instead of being n, fixed number of trials, this is t, the number of trials until we get the first success. So this is not fixed. So we just are going to keep rolling that die until we get a 6. So S is still the same thing, the success, the probability of success is the same. So as I roll a die, it's still only a probability of 1/6 chance of getting that 6. Okay, so we're going to just sort of use X for binomial and Y for geometric in this situation just to keep the two separate. So if we define a random variable y to be the number of trials needed until the first success, then we're looking at a geometric random variable and a geometric distribution instead of a binomial random variable and a binomial distribution. The number of trials y that it takes to get a success in a geometric setting is a geometric random variable. The probability distribution of y is a geometric distribution with parameter p, so that's the same thing as the binomial distribution. When you look at a geometric distribution, we're still looking at, we define it as NP. In this case, we're defining it as P, which is the probability of success on any trial. So the possible values of y, so the number of trials to get the first success, that's what y is 1, 2, 3, 4, so on and so forth. Just take note that they're all whole numbers because when I'm rolling a die, I can't roll a die like 2.5 times. I'm not going to get anything. All right, so it's just really important as you're reading these questions to distinguish between situations in which you have the geometric distribution and situations in which you have the binomial distribution. Okay, so let's take an example, look at an example of the geometric probability formula. All right, so the random variable of interest is, we're going to take a look at the lucky day game. The random variable is y is the number of guesses it takes to correctly match the lucky day. What is the probability that the first student guesses correctly? So that's saying we want our success on the first trial. The second student, the third student, what's the probability that the kth or the 5th, 6th, 7th, 8th, whatever student guesses correctly, that correctly matches the lucky day? All right, so what is the probability that you are going to, that the first student is going to guess correctly? Well, we know that we have 7 days out of the week, and they only we're matching 1 day, so it's like having a piece of paper and you have 7 of the days written down. What's the probability that the first student is going to guess correctly? Well, they only have a 1 chance out of the 7 to guess correctly. Okay, so y equals 1 is saying that the student is going to guess on the first trial. Okay, the success is going to occur on that first trial. So what's the probability that the student is going to guess that it takes 2 trials? So when we have y equals 2 here, it's a little bit different than binomial. This is saying it takes, the success is on the second trial. So what does that probability look like? Well, if they guess the first time, this is not, they can get 6 out of 7. 6 is not getting it correct out of the 7, but on the second trial they did get it correct and they have a 1 out of 7 chance on the second trial of getting it correct. So 0.1224. Okay, so the probability y equals 3, that means it takes 3 chances, okay, on the third trial is going to be when they're going to get it correct. So that means the first trial and the second trial, they did not get it correct, but on the third trial they did. So first trial, second trial, 6 out of 7 chance of not getting it correct. The third trial, they did get it correct on 1 out of 7. And you might be thinking, well, if P equals, normally I could move these, probabilities around. I could have the chance it would be the first and the third and so on and so forth. This is different. We don't have to use combinations to figure out the number of possibilities because I specifically only want it correct on the third trial. First two are failures and the third one is the success, okay? So, and this is just basically something that you've seen in your other probability questions. So if Y is a geometric distribution with a probability of P successes, how can I figure out what's a general formula that's going to show me when I'm going to get my first success? So when we have probability of Y equals K, that's like saying the probability that the guess is correct on a certain trial, on the fourth trial, fifth trial, whatever. It's 1 minus P. Okay, I usually flip this around. I usually use the probability of success. Okay. I usually flip these around, but that's okay. This is totally fine here. We're going to go over this on the next recording.